Here we have a problem on integration. That is, we have to evaluate this definite integral and round our answer to 3 decimal places. Okay, what I'm going to do is I'm going to evaluate the integration of this function without limits. So that is, I'm going to evaluate this one as an indefinite integral. That is integral e to the power of x divided by 1 positive e to the power of 2x dx. Once I get the result of this indefinite integral, then I'll take the limits, the lower limit 0 and upper limit ln 6 in the result of the integration we have over here. Okay, now what I'm going to do is I'm going to write this numerator as 1 by writing this e to the x power along with dx. Okay, let me write 1 over, and in denominator we can write this e to the power of 2x as e to the power of x the whole square times e to the power of x dx. Okay, now what we can do is we can go with u substitution from now, because here in this function, let's consider this particular part. So here, what is the derivative of e to the x power? The derivative of e to the x power is the same e to the x power. It is multiplied over here. In integration, whenever the derivative of a part of the function is multiplied with the function itself, what we can do is we can integrate such a function with u substitution. So now what I have to do is I have to substitute a new variable u for the part for which we have the derivative. We have derivative for this e to the x power. So now we have to substitute the new variable u for this e to the x power. Let me do it. Okay, when I substitute a new variable u, I have to get this complete integration in terms of the new variable u. When I get this complete integration in terms of u, at the place of dx, I must be getting du. If I want to get du at the place of dx, what should I do with this u? I have to find the derivative. Since we have the original integration with respect to the variable x, now we have to find derivative on both sides of this equation with respect to the original variable x. When I find derivative of this u with respect to x, I'm getting du over dx. When I find the derivative of this e to the x power, it's just e to the x power. Now, to solve for du in this equation, we can multiply both sides by dx. When I multiply both sides by dx, I'm getting du equals to e to the x power times dx. Okay, now let me apply the u substitution over here. Then I'm getting integral 1 over 1 positive. For this e to the x power, we can substitute the new variable u. Then I'm getting u square over here. And for this e to the x power times dx, we can substitute du. Okay, now let me consider a particular formula in integration, that is integral 1 over 1 positive x square times dx. Okay, the integration of this function is arc tangent of x positive c. Okay, now let me consider the function we have over here in our integration. It's exactly in this form, that is 1 positive x square times dx. Okay, so at the place of x, we have u over here. Then what is the integration, what is the evaluation of this integration? So it is equal to arc tangent of, so at the place of x, we have to write u. Okay, now I got the evaluation of the indefinite integral over here, but I got the result over here in terms of the variable u. U is a variable taken by us. It has to be replaced by the original stuff. So what is the original stuff? The original stuff is e to the x power. That we have to plug in for the u over here. That is arc tangent e to the x power. Okay, now I got the evaluation of the indefinite integral over here in terms of the original variable x. Okay, now what we can do is, now in this result, we have to plug in the given limits, lower limit 0 and upper limit ln 6. Okay, now let me erase the other stuff and continue the problem. Okay, let's continue. This is the result we got for the evaluation of the integration of this function. Okay, now what I'm going to do is I'm going to plug in the lower limit 0 and upper limit ln 6 for the result of the integration over here. Okay, let me do it. That is, the lower limit is 0 and the upper limit is ln 6. Okay, now I have to plug in this upper limit ln 6 for x over here in this result. Then I'm getting arc tangent e to the power of ln 6. Now I have to take negative sign. In the same result, I have to plug in the lower limit 0 for x over here. Then I'm getting arc tangent e to the power of 0. Then I'm getting arc tangent. Okay, now let's do some simplification over here using the properties of logarithm. Okay, let me consider a particular property of logarithm, that is a raised to the power of log x to the base a. Okay, so whenever we have an expression in this form, here the base is a, and we have a logarithm at the exponent with the same base. Whatever base we have over here, the same base we have over here. So whenever we have an expression in this form, so it is equal to the argument of the logarithm at the exponent, that is x. Okay, now let me consider this particular stuff, that is e to the power of ln 6. Actually, ln is a natural logarithm and its base is e. Usually, we will not mention the base e for ln. So, actually, its base is e. Now, let's consider the base over here e, and we have a logarithm at the exponent. And what is the base of the logarithm at the exponent? That's also e. So the base over here is e, and the base of the logarithm at the exponent is also e. So what is the result of this one? So it's just the argument of the logarithm, that is 6, according to the property we have discussed over here. So the evaluation of this e to the power of ln 6 is just 6. Okay, now let me continue over here. So instead of that, we can write 6 and negative arc tangent. Okay, so the value of e to the 0th power is just 1. And now we can calculate the value of arc tangent 6 and arc tangent 1 using calculator. Okay, when you evaluate this kind of inverse trigonometric functions arc tan 6, arc tan 1 using calculator, please make sure that your calculator is in radians mode. Usually in default, the calculator will be in degree mode. In that case, when you evaluate the value of this kind of inverse trigonometric functions, the result you are getting will be in degrees. Actually, degree is not a real number, it's a unit of an angle measure. But when we evaluate this kind of different integrals, the result has to be a real number. So to get the result of this different integral as a real number, we have to keep our calculator in radians mode, so that we'll be getting the answers in radians. Actually, radian is a real number. Okay, so when I use a calculator to evaluate this one, and also when I subtract these two values, I'm getting a very long decimal. But according to the instruction we have in the question, we have to round our answer to 3 decimal places. When I round my answer to 3 decimal places, I'm getting 0.620. So the evaluation of the given definite integral is 0.620.